Hello, I'm Bill Inman. I'd like to welcome you to the last day of our presentation on the Data Lakehouse. Today, we're going to be hearing from Jason Pohl and Sean Owens. Jason's going to be talking about the infrastructure that we have for the Data Lakehouse environment, and Sean's going to be talking about machine learning. So, with that, I'm going to turn it over to Jason.
All right. Well, thanks for having us here today. Um, I'm Jason Pohl, and I'm joined today by my colleague Sean Owen. We both work at Databricks, and we're going to tell you a little bit about the Lakehouse today and how the data lakehouse can help, fulfill all the use cases on a single data lake, everything from AI to BI. I'm Jason Pohl. I'm principal solutions architect. I focus on the data management practice here at Databricks. And prior to Databricks, a long time ago, I used to be a data warehouse architect as well. So I used to build a lot of data warehouses using popular ETL tools of the day. Sean, do you want to go ahead and introduce yourself?
Sure, happy to. Yeah, I'm a principal solutions architect here as well. At Databricks, I focus on machine learning and data science. By training, I'm more of a software engineer, not a data architect from long ago at Google, and focus on data science for about the last decade. So yeah, maybe I have a different perspective to offer on the needs of machine learning and how this maps to data warehousing and the lakehouse.
Excellent. So just to begin, I want to say, the future is here. It's just not evenly distributed. So when I say that, there's this massive consensus that CEOs around the world say AI is a strategic priority, and that if their company doesn't figure out how to apply AI to their business, then they will be left behind. And Gartner basically proves this out by clarifying that almost $4 trillion has been created in business value by AI, or will be in 2022. But on the flip side, this stuff is hard. Like 85% of big data projects fail. And I think if I were to, wind the clock back maybe 15, 20 years, you'd see the same rough number of data warehouse projects fail. So there's new technology is hard to get right. And about 87% of the data science projects never make it into production. So why is that exactly? And I love to show this data and AI maturity curve because it kind of like shows the evolution of where we're going with data and analytics. So whenever I was building data warehouses, I was focused a lot on, basically getting reports out the door. So getting data structured in a way where you could hook up a business intelligence tool and run reports against it and give those reports to the business. And eventually, there's all sorts of tools that popped up to be able to do ad hoc queries. So being able to slice and dice data on the fly. And really, when you think about it, what these tools were doing is they're allowing the business to kind of have a historical perspective on what has happened in my business. And then it was kind of up to the user to extrapolate from there using, their domain knowledge to figure out what might happen in the future. So now we're kind of like seeing this evolution where it's not good enough just to tell you what's already happened, but you want to be able to explore that data. So after you get these numbers, can you work with that data and do some exploratory data analysis to figure out, why did this happen? Maybe not just the slicing and dicing anymore, but taking that data set and joining it with other more interesting data sets that might be unstructured as well, and then trying to come up with some hypothesis. And then now you can apply machine learning or artificial intelligence to do some predictive modeling. So for all those different values that you've been looking at and querying, if you were to look at all the other data points around it, could you come up with a model that tells you what will happen? Can you predict, what your customer churn is going to be for a particular customer cohort, for example? So that's where things are heading. And up and to the right is prescriptive analytics. So once you have a set of predictions you've made about various business scenarios, can you recommend the best next course of action? So you can kind of see where these things are going. I mean, I've got a toy example on my phone that I use with my kids where I can take a picture of a whole bunch of Lego blocks that have been dumped on the floor, and this app can actually tell me what are all the different things I can make from the Lego blocks it sees in the picture. And it can actually then give me the instructions, step by step on how to build those things. So, I mean, it's a simple toy example that I use with my kids, but you can imagine, being able to take a picture of a car who's been in an accident and then getting an instant quote for how much money we think it's going to take to fix that car, or if it's just, going to be total. So this is the direction that things are moving. And the companies that figure this out are going to have a leg up on their competition who haven't figured it out yet. The other thing that's kind of changing is the notion of what is a modern data team. So, thinking back to my data warehouse days, we typically had ETL engineers and BI developers on the team, and we were servicing the data analysts ultimately. Well, we still have ETL developers, but they've kind of morphed into this new role of a data engineer. And we still have data analysts that we're ultimately servicing, but we also have data scientists now. So this is a kind of like a third leg of the modern data team that we didn't have before. And data scientists are people who can do, the traditional analysis the data analysts are doing, but they also use, other tools to create these predictive models. And so they're working not just with SQL, but they're also using popular tools or popular languages such as Python and R to be able to achieve these goals of making predictive models. So the vast majority of companies, they struggle to get this right. And why is that? There's some companies that are doing excellent at it. And these are, if you look at the top 1% of the Fortune 500, these are the FANG companies like the Facebooks, the Alphabet, Google, Netflix. They manage to harness all the data within their grasp and turn it into insights that they can then, monetize more easily. So why are other companies struggling? And I think if you were to look, it's because of, the legacy technology stacks that they have to deal with. So if you look at the different silos of data and use cases that people are doing, you've basically got, data warehousing to do the historical analytics, data engineering, which is, traditional ETL, but also using, technology to be able to handle unstructured data and maybe doing it in a streaming fashion. So you've got a streaming silo if you've got to have real-time insights. And then data science and ML. So taking, all that data and making it accessible so that you can build predictive models and apply that in real-time production. And there's all these different systems and different technologies that these different siloed teams are using to achieve that. And they're all like a little bit different in their own way, and getting them integrated and hooked up can be difficult. So what happens is you've got siloed technology stacks, and now you end up having siloed teams as well. So data analysts, data engineers, data scientists, they're all kind of like working in their own world, and collaborating becomes difficult. So if you're all these different stacks, there's a lot of friction whenever you go to move your work product from one end to the other. So if you're creating a machine learning model that you want to put in production, data engineers have to get the data ready to train the models. And then after you've got a model, you need to push it into production. But if you want to do that in a real-time way, you're going to have to re-architect everything unless you figured out, a more streamlined, unified way to do it. So where does all this complexity really come from? It's, from this historical evolution of data warehouses versus data lakes. So if you think about it, you've traditionally had data warehouses that have existed successfully for many decades. And then you've got data lakes on the other side that have kind of come up in the recent, I would say like 10 to 15 years. And in these, just to kind of compare these side by side, the difference between a warehouse and a data lake, warehouses have traditionally been very proprietary. So, the code that you write for an Oracle, data warehouse doesn't necessarily work on a Teradata data warehouse. Whereas data lakes have created, from the ground up to be open. So they became most popular because of the open source project Hadoop. And they've evolved, over time as the cloud has kind of taken over from on-prem data centers. So now you've got most people building their data lakes in the cloud on top of cheap object storage, and then using various engines on top of that, like Apache Spark, to be able to process that data. Incompatible interfaces, so warehouses, you can basically just use SQL for the most part. But with data lakes, you can use more interactive exploratory languages like Python. So I think when I first started Databricks, 6 years ago, R was kind of like, I think, the most popular language around, data science. And I think Python is, quickly taken over. So these things kind of changed for a bit, but, the expressiveness of being able to work with your data in a data frame interface, which is what, Python and R use, just gives you a lot more flexibility than you'd have with a warehouse. And I think one example of that is, if you ever needed to do master data management or record linkage, sometimes we call it entity relationship or entity resolution, it's really hard to do that with just SQL alone. You need to be able to bring machine learning algorithms to be able to map certain people to know that Bob Smith is the same as Robert Smith, for example. And then incompatible security and governance models. In general, data warehouses were all table-based. So all the governance was done based on tables and columns and being able to apply even like cell level security. Whereas data lakes has been, file-based from the ground up. So all of the governance around data lakes has historically been around who has access to which files, which directories, and then it's very coarse-grained. So if you wanted to apply any sort of fine-grained governance beyond that, you have to, come up with your own solution. That's why the data lakehouse is really taking off, because you can essentially write all of your data into one place, that place being the data lake, and then you can perform all of your different use cases on top of it. So you can apply streaming analytics, you can stream data straight into your data lake. You can apply, you can do your SQL BI, business intelligence reports on top of that data lakehouse. You can build your data science routines, which historically the data lake has been used for data science, because to build some of these models, you need to get very granular data and have access to lots of it and be able to process that in parallel. And then and the same with machine learning. So I think one of the things that's changed in the last few years is that people have been kind of building towards this for a while, but we've just recently hit this inflection point where you can have performance on your BI queries on top of a data lake, and it's just as good, if not better, than a data warehouse you might have built in the old days. So we believe the data lakehouse, it offers a better path. So it's a lake first approach. It builds upon where the freshest and most complete data resides. A lot of companies have built both data lakes and data warehouses side by side, and the idea was that you would land all your data in the data lake and do a bunch of your ETL there, and then you would load a subset of that into your data warehouse. But keeping those two things in sync is, requires a amount of energy and maintenance. And, you end up with like a bit of a lag, because the data in your data warehouse is never as fresh as the data that's in your data lake. We can do AI from the ground up on top of this data lake, and we can provide high reliability and performance, largely because we're built on top of the cloud when we're building these lake houses. And we want to have a single approach to managing that data and support all the different use cases. And one thing that's really important is to have a true data lakehouse, you have to build on top of open source and open standards. And this is pretty powerful, because there's a number of engines that can connect to a data lake or a lakehouse and execute queries. So Apache Spark is famous. Databricks has created Photon. There's Apache Presto and Trino out there. So there's all these different engines that can basically connect to the same repository of data and run queries. And some of those engines might be like better for certain types of queries than others, and some of them will become more popular and fade away. But you don't have to move your data out of your data lake to another system to take advantage of it. Your data stays in the same place, and then you just connect the best engine towards it. And it gives you a lot more flexibility, but also insulates you from being locked into any one particular engine or vendor over time. So today I'm gonna go through basically the first four areas here, and then I'm going to pass it over to Sean for the machine learning. But I'm going to take you through the foundation of the data lakehouse and the architecture, how to do modern data engineering on it, showing you analytics and data warehousing on the lakehouse, and then finally following up with governance on the lakehouse. So the data lakehouse foundation is really built upon this technology called Delta Lake. Delta Lake, it's an open source technology. And what it is, it's a way to apply ACID transactions on top of a data lake. So when I first started talking, I mentioned how data lakes were built with file-based access controls in mind. So when people first started developing on data lakes, they had to really think about what are the files that I'm writing out to this data lake, and what are the files that I need to read whenever I need to run a query. And then if you were to basically be writing out a large amount of data to your data lake, and that ETL routine failed halfway through, you might end up with like some files that have been committed and other files that were either partially committed or not quite done. And then you'd have to, manage that and roll it back. And likewise, if you had people who were trying to query that data lake at the same time, you'd have to manage that situation. And what it meant was that most data lakes, people would load them at like 2 in the morning, and then they would just get queried once a day. And it kind of like impacted the ability to provide real-time analytics on it. With data warehouses, you had the ability to have transaction control. So, you wouldn't consider any data committed until you've actually hit that commit point of the transaction. But data warehouses tend to like be very good at loading a bulk amount of data, but not really like streaming data in. So what Delta Lake did was it provided a transaction layer, so you could have asset quality transactions on top of Data Lake and be able to write data to it at the same time as other queries are querying it, and then also provide performance optimization so that those queries become faster over time. So to kind of summarize some of that, reliability and quality. So with data lakes, if you're having to worry about what individual files you're writing, you're going to have to build a lot of boilerplate code around that to be able to manage it reliably. With Delta Lake, you get ACID transactions. Performance and latency. So if you're just dealing with files on a data lake and you wanted to query those files, what you'd have to do is basically list out all the files in a directory and then maybe read in part of those files to figure out if the files have the data you're looking for, and then do additional filtering. With something like Delta Lake, what you can do is we'll capture all the statistics of the columns that get written out. And then what we'll do is when you go to run a query, we can determine from looking at these statistics, which files do we actually need to read to satisfy this query or not, and then have a much shorter list of files to read. And so this type of optimization is really like indexing. And we can apply indexing to a data lake and make the queries go much faster. And then finally, governance. There's challenge when you're trying to govern files, because if you have, if those files represent a table of data and you've got some sensitive data in there, you might want to govern, 5 of the columns in that table differently than the other, 30 columns. So being able to do fine-grained governance is really important. And you can only do that if you have like a logical table level rather than trying to do it at the file level. So Delta Lake has been, it's one of several different technologies out there that really enable a true lakehouse. Something like Delta Lake is the difference between having a data lake and having a lakehouse. And Delta Lake is already in use of thousands of customers. I think just on Databricks alone, we process exabytes of data every month using Delta Lake. And it's got a broad industry support because it's open source. We've got different connectors that have been built by the community to help, read Delta Lake tables from, all of the engines you see over here. So Apache Spark, Presto, even, Snowflake and Azure Synapse, they can load and, create external tables that map to Delta Lake tables. So what can Delta Lake do for you? It's going to scale your data insights throughout your organization. It's going to provide, the best price performance, because in the cloud, you can separate not just compute from storage, but you're separating how you pay for your infrastructure. So in the cloud, you spend money based on how much data you have, you want to store in the cloud on the object storage. And then you only pay for the amount of compute for the amount of time that you're using it. So if you wanted to, I think back to when I was building data warehouses, we'd have customers that have, 30 years worth of data. And when you look at the queries they typically run, it's maybe for like the last 5 years worth of data. And so, how much data would you choose to keep in that data warehouse? Maybe 10 years, the last 10 years. But then what do you do with the other 20 years? You archive it off somewhere and hope that you can, import it into your data warehouse to run queries if you ever need to. The beauty of the cloud is you can keep all 30 years worth of data, on object storage because it's super cheap, like I think 5 cents a terabyte. And then, you can basically just spin up the size of the cluster that you need to do the processing you need. So if you wanted to run a query that processed the last 5 years of data, you might have a medium-sized cluster. And if you wanted to process the last 30 years of data, you just spin up a bigger cluster. And then whenever you're done doing the processing that you need, you just shut that cluster down. It doesn't have to stay up 24 hours a day. And Delta Lake is, the foundation for being able to do this. So now I want to do a little bit of a demo. So in this demo, I'm gonna go through a little bit about and show you, what Delta Lake is doing. And I'm going to be using a Databricks notebook to do that, but I'll walk you through as I'm doing it. So just to kind of set this up, we've got some loan data here. So this is loan data that's it's all public data. It comes from Lending Club. And you can see it includes all the funded loans from 2012 to 2017. So these are just files that show up as CSV files. And what I'm going to do is I'm going to create a Delta table. So I'm just using regular SQL here. I'm going to create this table called Lending Club Delta. And it's going to basically create a table with an ID and a bunch of columns. And it's loading it from, this is it's not CSV data, I guess, but it's just Parquet data. Parquet is a binary format. It's an open source format that's used to store data. So it's if you ever want to run queries that sum things up, it'll perform much quicker on Parquet than it would on like a CSV file. So I'm basically reading data from that Parquet file, applying my own unique identifier, and then saving it as a table called Lending Club Delta. And you can see here it's computing a snapshot. So because Delta creates this transaction log, it's basically every commit has its own version number, and then you'll see how we use that version number later on. So here's the table I just created. Now what I want to do is I want to stream in some data to this table. So I'm going to create this temporary view, loan by state read stream, and then I'm going to basically run a query on it. So I'm going to run a query that basically looks at the total loan amount, and I'm going to group it by the state. And then I'm going to do a visualization where I take that data and I show it on a map of the United States. So you'll get a sense of, it's kind of like a heat map. How many loans are being, I guess, originated, per state. And you can see this stream initializing. So I'm essentially starting up a streaming query, as we call it. And that streaming query is using Apache Spark structured streaming. You can basically stream results from a query as it's coming in. So here it's initializing. And then once that stream is up and running, it essentially, will continue to check, for new data every, I think, 10 seconds or something like that. So you can kind of see here, in the darker, so California has the largest amount of loan origination. Texas has got, second amount. And then Iowa doesn't have any loans. So let's see what happens if I were to insert some new data into, my table. I'm just going to insert some data that says that Iowa has got, some loans that have been originated there. And so what I'm doing is I'm running a query in real time on my Delta Lake, and then I'm also inserting data into that same table. And I'm basically using the power of ACID transactions to be able to read a consistent state at all times, the same time as somebody is using DML statements to modify that data, in this case appending. And my streaming query just updated, so it registered that something has changed in the data that it was reading, and now I've got looks like there's a lot of loans being originated in Iowa all of a sudden. So maybe I'd had some bad data in my pipeline, and I found it and then fixed it. So you can do lots of different things with Delta Lake. It's not just delete statements, but it's full DML support. So here I'm going to basically just delete everything from that table for where it relates to the state of Iowa. So I'm basically just deleting the data I added. I can also update. So I can run update statements. You can essentially run all the DML statements you'd expect. So inserts, updates, deletes, merges. And what I'm going to do here is I'm going to create a staging table with some dummy data. I'm going to call that staging table load updates. So I'm just creating like 3 records in here. And then it's putting that data out onto my data lake and registering it as a Delta Lake table. And then what I can do is I can do a merge statement. So I'm going to take the data that's in that load updates table I just created. I'm going to merge it into my Lending Club data. And this is all happening while that streaming query is still running. And then I've got a little bit here in schema evolution. So one of the great things about data lakes in general is you can evolve the schema over time. So if you're bringing in the same data every day and it's got 10 columns, and all of a sudden your upstream system adds a new column and adds that 11th column, with a data lake, you can basically identify that and then add the additional column into your Delta Lake table and then continue the load. So you don't have to have these, big cost per column, projects I used to call it, where you want to add a single column, you have to, update the schema, update all the downstream schemas, and then update the BI reports. You can have that additional column flow through in your ETL. And then basically, when you need to, you can add constraints as well. So in this case, I'm going to add a constraint on this ID column that we created. I'm going to make sure that it's never null, basically. So you can add constraints to help with data quality on your Delta Lake. And then if I'm going to purposely try to add some data that doesn't have an ID, and it's going to tell me like, hey, you're violating this constraint. So it's making sure that bad data doesn't go into the table if I don't want it to. Now, the other good thing about Delta Lake is that because you've got this transaction layer and you're essentially monitoring all the different changes that are made to your data, you have like an audit trail or breadcrumbs where you can go back in time and run a query as of a certain point in the past. So if I look at, if I describe the history of this table that we've been working on, I can see that there's 5 different versions, version 0, 1, 2, 3, 4. You can see at what time, a change was made, what was the operation. So in this case, we're creating the table, writing to it, deleting, merging, adding a constraint. So both the DML and the DDL are recorded in this transaction log. You can see exactly what were the parameters, and even like what notebook ran it, what kind of isolation level, and then the individual bits of data, or how many files and rows were added or removed. And this becomes pretty powerful. So if I wanted to look at this one, I can see, so this query, what it's going to do, it's going to sum up, the origination loan amount for the state of Iowa. And you can kind of see over time how this changed. So there was nothing in version 1 in version 0 when we created the table, so it doesn't show up there. And in version 1, that's when we added that Iowa amount right when we started the streaming query. So you can see it got added there. Then we deleted it, so it doesn't show up until version 3 when we add it back. So you can kind of see, the changes to your data over time. And if you wanted to run a query as of a point in time like version 3, you could do so. And that allows you to do things like rollbacks. So let's say that you realize that we had an ETL run and it had like so many bad errors that we just want to roll back, fix the ETL, and run it again. You can use what's called a restore command on Delta Lake to restore that table and roll it back to a certain version. So in this case, I'm going to roll it back to version number 2. And if I do a quick query, what's the total amount for Iowa? It's 0. So I've essentially, rolled back to a previous version when we didn't have any Iowa data in there. The other thing that is kind of interesting, because you've got this transaction log, what you can do is you can query the table. I've got this function here called table changes. And I'm basically saying, give me all the changes to the table since the beginning of time, version 0. And this is basically really good for change data capture. So I can see all the changes that were made to this table. So based on this this ID, what changed exactly, and what was the commit version when this happened. And I'm seeing a lot of deletes here because I essentially just did a rollback. But you can use this to build in your ETL so that when you're going from stage 1 to stage 2, you can take advantage of the table changes function. So that way you're only capturing the changes that are made to the table since the last time you ran your ETL, rather than having to rely on last updated date columns, which, it's helpful. But if you ever delete data in your table, you're not going to capture that through just those user columns. You got to have something like change data feed to do proper CDC. So that's a little bit of an intro on Delta Lake. I'm basically just running, regular SQL commands, but I'm running it against tables, a logical layer. And underneath, Delta Lake is doing all the hard work of figuring out what files need to be written, what files need to be deleted, which files are considered, committed versus not. And I don't have to think about any of that stuff. And I'm doing it all in SQL, but you could easily do it in, in Python, Scala, or R as well. All right, so next, I'm going to talk about modern data engineering. A lot of the work I used to do with data warehouses, it was, I was an ETL engineer, so I was doing a lot of ETL. Now I feel like a lot of the work that ETL engineers were doing, it's more or less the same, but we're calling it data engineering now. And there's a little bit of a difference too, but I'm going to go through it. And this just kind of shows that, on a single lake house, you've got the different types of use cases at the top. And in this case, we're going to focus on data engineering. So the problems with today's architectures is it's cheap to store all the data, but if you were to basically have a data lake and a data warehouse, it gets more complex. So you would have to basically have some sort of synchronization process that loads data from your data lake to your data warehouse and keep that in sync and run it reliably over the course of time. And anytime you have like an extra hop, you've got an opportunity for things to go wrong or to get out of sync. And also it's the timeliness. So I call it the data freshness. But if you've got 2 or 3 hops to your data, the first hop is always the freshest, but it may not be the easiest format to query. And then the last hop is probably optimized for certain queries, but it's not as fresh. So you basically have these trade-offs. If you can just write everything once to your data lake and have a query engine on top of it that's optimized to query it, now you don't have to have all these multiple hops. And furthermore, you don't have to pay to duplicate the data. If you've got all of your data in a data lake and you've got some of that data in a data warehouse, you're actually paying to store this data twice. And with modern clouds, there's like, I think Amazon's S3 storage, it has like 11 nines of durability, which means essentially like you never have to worry about, a bad hard drive causing loss to data, because Amazon has a team of people who all they do is go up and down the racks of data centers every day, look for bad hard drives and take it out, plug it in. And they've got replication factors to make sure that your data is safe. Now we want to make sure that we talk about open formats. So within that that blob storage or the object storage on a cloud, you have to write out files. Now in the early days of data lakes, people were just writing out CSV files, but those turn out to be very, very bad for performance when you go to query them. Also, if you've ever worked with CSV files, it's very easy to corrupt them. If you're delimiting your lines by commas and you pull out a field and somebody put a comma in that field, now everything's off. So CSV files just turn out to be like really difficult to manage. And so there was a couple of different open source formats that came out. The first one was ORC. This was created by Facebook. And the other one was Parquet, which was I think a partnership between Cloudera and Twitter. And these open source formats are basically binary file types that store the data in a columnar format. And it ends up, one, making sure that you don't have that problem where somebody put a column in a field and now everything's off by 1. But 2, it allows you to store the same amount of data in a much more compact and small amount of space. And 3, it allows you to run queries on top of that data. So typically with a data warehouse style query, you'll say like select these 5 columns, sum up this other column, group by the first 5. And it might be from a table that has 50 columns in it. So if you're being very selective about the number of columns you're pulling out, you'll get much better performance on something like Parquet, where you can only scan the file for those 5 columns, for example. And these open formats, they become so widespread that almost every BI tool out there as well as ETL tool today on the market that can read and write to Parquet formats. So, but the question is, can we get state-of-the-art performance and governance with this design? Historically, people have thought, I don't think so. But now the Lakehouse provides that. So this is kind of this has got a lot of stuff on this slide, but it's basically meant to show like these are all the main components that you would expect when it comes to data engineering on the Lakehouse platform. And if you think about, if this was 15, 20 years ago, we're building a data warehouse, a lot of these terms are the exact same. So you need to, get the data into your data warehouse, right? Today, we're talking about getting data into the Delta Lake or the data lake. So that's data ingestion. But that used to be the E and the L part of ETL. You want to make sure that you have this open storage format at the bottom. So in this case, Delta Lake. You're going to usually have, a DAG or a graph of different operations that you need to execute on. And you're going to need some sort of scheduler or orchestration tool to do that. You're going to need to transform the data. This has either been done traditionally with PL/SQL routines on the data warehouse or with external ETL tools like Informatica. But more and more for data engineering, people have used open source tools like Apache Spark to do this data transformation. And likewise, lineage and end-to-end pipeline visibility. These are things that especially if you're in a regulated industry, you're going to need these things. And essentially, with data engineering, I think the thing that's different about data engineering today compared to ETL many years ago is like when I was building data warehouses, I almost always was pulling data from another database, another relational Oracle, SQL Server, or DB2 database. But now the type of data you're getting is much more diverse. So it's not just databases, but there's a lot of JSON. Some of that JSON is coming in from streams of data that you have to process on a continuous basis. There's a lot of online SaaS applications that people want to pull their data out of. So whenever I extract data out of Salesforce, I'm not just connecting to a database anymore to pull that out. I have to connect to REST APIs and do repetitive calls to get the data and then put it someplace else. So there's just a lot more different data sources that people are getting. And there's also unstructured data too. So there's, I worked with one customer who, they were an advertising agency and they wanted to do some analysis to show which, for their particular client, which is a soft drink manufacturer, could they look at social media pictures, find the pictures that have a picture of their soft drink in there, and then look at the demographics of the people in the pictures to figure out how can they better market their product. So that's the type of use case where you're not going to be able to do that with just a data warehouse alone. You need to handle unstructured data. You need to do it in a scalable way. You're going to need a lakehouse for that. And that's reflective on the right side, the data consumers. These are the types of use cases that you're going to do. Ultimately, a lot of these different types of either dashboards or analyses, you'll hear the term data products. That's becoming more and more of the term that people want to use as data products. And to kind of like give you a little bit of a sense of the architecture that we typically recommend, you will see like data going in these different layers. We call it the medallion architecture because it's almost the Olympics again, right? So you got bronze, silver, and gold. But I think really these are just different stages that you would typically apply in your ETL. And the bronze stage is really about, I want to make sure that I capture this data and as close to this same format as I got it in, and make sure that I do it in a consistent, reliable way and not put any strain on the source system I'm getting it from. And the gold layer, you want to make sure that you're organizing, structuring, and indexing this data in a way that's going to serve up the end user queries as fast as possible. So these are typically like aggregated tables that have constraints on them to make sure that you're getting very clean data in there. And then the silver is kind of like everything in between. It's like the all the stages you have to go through to go from like raw data to presentable data. And as you go from left to right, the quality of the data is improving because you're applying business rules. And then you're also just making it more and more, you're applying more and more business rules to make sure that nothing is getting to the gold layer that you wouldn't expect. But the reality is not so simple because I just showed you one pipeline, but there's actually like lots and lots of different pipelines, and there's using lots of different data sources. Some of these sources are files. Some of them, are going to be queues like, Apache Kafka. And so what happens is you have this large scale ETL that you're running across your business, and it gets pretty complex pretty fast. So you got to like worry about all these different dependencies. So if you're loading a fact table, did you load all the dimension tables first, and then did you load all the staging tables that you need to normalize before it can load those dimension tables? It's difficult to switch between batch and stream processing. The data quality suffers because you have to make sure that the data that you're running is adhering to the business rules, and if something new shows up, that you're aware of it. And it makes it really hard to trace all the lineage if you're not doing this in a combined way. So now I'm going to go through a little bit of like what's the best practice for doing modern data engineering on the Lakehouse. So I'm going to introduce something to you called Delta Live Tables. So it's a simple way to build and manage your data pipelines for fresh, high quality data. And in this example, we're going to show how basically you can bring in some raw data, transform it, join it together, and then apply some machine learning against it to score something. And then ultimately it feeds a gold table that's going to be used as the backing for a dashboard. So what we do is for the files that are showing up, we use something called autoloader or cloud files. And there's a bunch of JSON data that's being ingested. And the nice thing about the cloud is you can land files onto cloud storage, and it doesn't matter how fast you want to write them or how many of them you want, because the cloud is not infinite, but it can scale pretty much infinite. So you can have as many of these JSON files coming in as you want. And then what we do is we make sure we leverage some of the native services on the cloud to be able to be notified that a new file has been written to the cloud, and then automatically start processing that file using our pipeline. And what we do is by including this word incremental, we're going to create a routine that it's going to load from the data source, these JSON files. And then after that pipeline has gone all the way through for one micro batch, it's going to go back and check it again and just incrementally keep loading it. And you can see we've got this constraint we applied on the table. This constraint makes sure that there's this hidden column called underscore rescue data. We want to make sure that that's null. What the rescue data does is, if you've got an expectation on how you think your data should be from a data source point of view, and that expectation changes for whatever reason, like we get, you were expecting to get like an integer, and all of a sudden a decimal shows up. What it'll do is it'll write that column and the decimal value to the string column called rescue data. And then you can go back after the fact and look at, why did I get a decimal all of a sudden when I've only ever gotten integers before, and decide how you want to handle that. Maybe you end up truncating that value, or maybe you find out that now you got to have a decimal in your table. The point is, though, you can basically automatically capture that, keep your ETL running, and then add a constraint to say that, hey, I expect this to never happen. And then I'll show you what happens with those expectations later. So now we're going to go into the silver layer. So this is, the silver layer is, could be one stage or it could be many stages, but essentially you're applying some business logic and data quality to it. So what we're doing here is we're creating another table called user silver DLT, and we're adding another expectation. We think this ID should never be null, so we're adding that. And then basically creating this table, adding a comment, so you can actually embed your documentation. I think this is like an overlooked feature, but I love this. So you can essentially add comments in line with your code, and then as you run your ETL, it's going to register these tables and then add the metadata about the comments, and then you can go back and look at that metadata, and also you can search for it. So if you do this, if you're really good at like making sure you self-document your code, whenever somebody goes to search for data sets, they'll be able to index and search on these comments, and now you'll be able to discover that somebody else in your organization has already created the table that you were about to create yourself. Here we're just applying some timestamps. And then, so now what we're going to do is we're going to ingest another set of data. This is spend information using the same routine as before. The first set of files were JSON files. These are CSV files. And you can kind of see here on this diagram, now we kind of went down this route on the right. Now we're going down this route on the left. Now we're going to join those two table sets together in the gold layer. So we're joining these two streams together to create one single gold table. And finally, we're going to enrich that first gold table with information from machine learning models. So we've got a model we've created with MLflow, and we're basically going to register that model and then take data that's coming through that pipe, run it through the model, get a score, and then write that score out. All right. And then by using this stream function, this is the final table in our live table pipeline. It's going to basically signify that, hey, I want to run this on a continuous basis. So I'm going to use the stream function. So you can actually have this pipeline run in batch and then schedule how often you want it to run, or you can just run it as stream and have it running all the time. And then what happens is whenever you go to create this or execute this this notebook, it generates this for you. So we didn't have to, open up some tool and drag and drop boxes on the screen and then say what this box was, and then it depends on this other box. What happened was Delta Live Tables figures out like, hey, I want to create this final table, and it depends upon this other intermediate table, which depends upon these other tables that joined, and this one depends upon another bronze table that loaded. So it figures that all out for you, and then you can run this in a continuous fashion. So we have different ways to run these in either development or production. Development just means that I've always got the cluster up and running, and I can iterate on it. Production, typically for, if this was a batch job, you would want to run this once, and then, to do that, you spin up the infrastructure, you spin up the machines you need, run that pipeline from start to finish, and then shut it down afterwards. And that's what the production mode does. And I can see from running here, like, what the cost of it is, what cloud I'm running it on. If I need to troubleshoot, I can go into the Spark UI or look at the logs. And then from here, I can see, a log of, hey, was there any trouble in running this? Every time every time it tries to do something and it gets a failure. So in this case, I got a warning. There was an unsupported operation because some of the magic commands we had in that notebook weren't supported for the cluster we were running it on. And, for the most part, everything is green. I can filter if there's any errors or warnings, but this gives me an easy way to look at, all the complex operations that are being done and if they're successful or not. And then the other thing we can do is, because we put in those expectations or those constraints to watch for data quality checks, that ends up feeding a Delta table on its own. And we've created a dashboard that you can just point to and look at these things. So we can monitor our pipeline in real time and see that, we had like, over 3 million rows ingested every day. And our quality failure rate was, there's about, a little bit over 5% of our data was, not adhering to our rules for whatever reason. And then about, 0.1% had an invalid schema. For each of the tables I have listed here, I can see, what's the quality score. So it looks like this one, the gold table has 75% pass rate, but 12% of the records were failed and then 12% were dropped. One of the nice things about these expectations is you can choose what do you want to happen whenever an expectation gets violated. So with a lot of ETL, if a business rule fails, it fails the whole ETL pipeline, and that's why you get paged at 3 in the morning. But a lot of times, it's only like 1 or 2 records that are failing a pipeline. So you don't want to like fail an entire pipeline because one or two bad records. You want to know about those 1 or 2 bad records and be able to take action on them after the fact, but you don't want to, fail everything at once. So Delta Live Tables gives you the flexibility to decide like, hey, do I want a hard failure? Do I want to just capture this and be notified about it? Or do I want to quarantine these records and then do something with them later? And you can see over time here, what's the daily error per expectations. Looking at a graph like this, I can, visually, I can see like, oh, it looks like everything was going along pretty well until, October 10th. And now, something started there and it started to get bigger. I probably want to, start to do some investigation on why that is. So this kind of like summarizes how you can basically do your ETL on your data lake using, on your lakehouse really. And, with the power of Delta Lake, you can essentially make sure that you've got ACID quality transactions on top of your data lake. And with Delta Live Tables, you can basically just focus on, writing a series of SQL statements. And, whenever you go to execute them, they figure out exactly, what are the things I need to do and what order do I need to do them to achieve this ultimate goal. And when you think about it, this final table that we're creating that people are going to be querying, essentially you've kind of created a materialized view at that point, and it can be as more complex in a materialized view than you would expect in a traditional data warehouse, because you can apply, machine learning scores to it as well. All right, so we went through, Delta Lake for the foundational layer. We talked about how to do data engineering on top of that data lake. And now I'm going to show you how you can do data warehousing on top of your lakehouse. So going back to our diagram here, we talked about, the core data engineering use case, but a lot of what people want to do on their data lakes is analytics and historical data warehousing type queries, which historically has been difficult to do on data lakes because there hasn't been, the right query engines to be able to give sufficient performance. But we've now hit this inflection point where, it's as fast, if not faster, than data warehouses. So recently, Databricks did a benchmark of the TPC DS benchmark, which has been out there for a very long time. And we broke the world record. So we beat the former holders, which were Alibaba, who used very specialized hardware. We were able to basically prove that you can get, faster performance using a Delta Lake Lakehouse, and do it cheaper than the existing record holder, which is Alibaba, using this technology. So we basically hit the inflection point where it is faster now and better from a cost performance to use a lakehouse. So just kind of show you what this looks like is you want to get, we've built, our own dashboarding capabilities within the Databricks, but most people are already using popular BI tools. So if you're using something like Power BI or Tableau, MicroStrategy, you can connect that to your lakehouse to be able to run queries on it. It's basically your BI tool is connecting to a SQL endpoint, which then is, the front door for an engine that's going to be doing all the calculations and all the queries. And more people, I think vendors are going in a serverless direction. So you'll see the word serverless come up a lot. Serverless essentially means that, you don't have to think about the infrastructure anymore. So you don't have to think about necessarily what are the types of servers I need and how many of them do I need and when do I start them up and when do I shut them down. With serverless, you have the ability to instantly have compute when you need it. So you're leveraging the capabilities of the cloud where you're only paying for machines for the amount of time that you're using them. But because it's so fast to get those machines and to give them up, you can basically do that at a moment's notice without having to have a bunch of machines up and running all the time, which is, what data warehouses have been doing for many years. So SQL analytics, you want to be able to do analytics on your lakehouse for historical reasons. So most people are using SQL for that. And we want to get, world-class performance for it. You also want to have like simplified administration and fine-grained governance. So you want to make sure that you can give access to your data analysts and do it in a way where you're only granting access to this group of analysts for the type of data that they should have. And the nice thing about doing your analysis on the lakehouse is that now you're doing it against the freshest data. You don't have to wait until the end of the day when it got loaded to a data warehouse. You can do it, on the lakehouse as it gets streamed in. And this just kind of shows like all the popular BI tools that have been out there. You can still use them. And there's also another class of tools that have been created to do the ingest and ETL. So DBT it's an open source framework that's becoming more and more popular. And what it does is it allows you to basically write regular SQL for your transformation logic and keep it in a set of files that are in a commonly accepted structure. And then what you do is you can run that SQL against a SQL endpoint on your lakehouse, and then it does all the transformations. So and because it's open source, it's becoming very popular, and there's lots of different projects that have been built around it. So that's a very common way now that people are using to do their ETL on top of the lakehouse. And you want to be able to use ANSI SQL on top of your lakehouse as well. So I'm going to show you a query where we basically fire up a dashboard And then behind that dashboard is a set of queries, and all those queries are running on top of the lakehouse. And then generating a bunch of dashboards that you can then collaborate with people and share out. And for the simple administration, whenever you go to spin up an endpoint, you basically just have to give it a few simple parameters. So you give it a name, you say like roughly, how big do you want this to be? Small, medium, large. And then you basically can add tags to it, and then you assign it to different groups. So unless you're in a particular group, you won't be able to connect to that endpoint. And if you think about it, you can create separate endpoints for your ETL and your BI users. So whenever I was building data warehouses, typically the ETL would run at night at like 2 or 3 in the morning. So that way the processing that we were putting on the data warehouse didn't interrupt any of the BI queries that were happening during the day. And that was one of the reasons why we were limited in how much we could put on there. With the cloud, because your resources are almost infinite, you could have one SQL endpoint that's running all of your ETL, whether it's batch or streaming, and that can be up and running at the same time as you have another SQL endpoint that your BI users are serving. And so essentially you've completely isolated these two groups of users, and they're not going to be stepping on each other's toes. And if you have a lot of BI users, maybe you want to give like a separate endpoint just for like the finance team. And now the finance team, because they're heavy users of these BI queries, they can be isolated from the other users in your organization. So there's no limit to how many different groups that you can isolate, and make sure that you're not having to make choices about architecture because of how many users you have. You can easily scale up as you need to add more users and groups. All right, so going into the demo here. So the DLT pipeline, the Delta Live Table pipeline that I was creating, it was ultimately, feeding this dashboard. So if I were to look at this dashboard, you can kind of see this is a global sales report. This was all the data that I was bringing through my pipeline and feeding into that gold table. I can see, very quickly how many orders are being fulfilled. You can imagine if this is, happening in real time, that those orders are going up throughout the day, how much cash is generated. You can also see like, how many customers are at churn risk. So I was, as that data was moving through the pipeline, I was calling a machine learning model from MLflow and scoring data and giving it a score to see like, hey, is this customer at risk of churning or not? And then also I could see how many products that came through were misclassified that were wrong. I can also, from a map point of view, see, where is this data coming from? And so these are just examples of the different types of panels you can include in a dashboard. And behind each of these is a query. So if I click on one of these panels, I can go to View Query, and I can see, exactly what's running behind. Oh, this one's not as impressive. Let me try one down here. So you can see this is just a regular SQL query that's being run, and it's using ANSI SQL. If I wanted to, I can look at different visualizations. So this one query is actually serving up 2 of the different visualizations we have in that dashboard, and I can still look at the raw table as well. I'll go ahead and run this again. I don't know if my endpoint is up or not, but you can kind of see, oh, it just ran. And let's see, if I were to look down here, you want to be able to, if this was like, if this was a long running query, maybe I've written my query inefficiently or it's running against too much data, I can easily go into here and look and see like, where am I spending my time when I'm running this query? And where is it running on? I can also look at the profile. So, okay. So you can easily troubleshoot your queries. And if I wanted to, I could create an alert as well. So you can create an alert looking at, if I were to look at that one query, I can trigger this query to run on a regular basis. And if the threshold gets exceeded, so maybe I'm expecting, let's see, this column, if it has a threshold over 1, if that happens, then go ahead and, in this case, I could send an email. Let's see, I could, let's see. Here we go. So from here, I can have it send an email to myself, or there's a number of other distant destinations. So the power of this is like you can be alerted in Slack or other places that, hey, some key business metric that you wouldn't expect to drop or exceed some threshold has done that. You should go take a look. And this gives you a way to, hopefully find any problems that might be in your pipeline before they get to the end user, but also just be alerted if, something interesting is happening in your business. And we talked about the SQL endpoints. So with the Lakehouse, you're going to have some sort of endpoint into that for SQL. With a database, you've basically got like one connection that you're establishing a JDBC connection to. With these SQL endpoints, you can have as many of them as you want, and they're essentially like connections that are in front of a load balancer. So you can have a load balancer who, as they take these connections in, it'll like share it out to multiple different servers, and you can make sure that everything is scaling. So this is with the Lakehouse and the cloud underneath it, you can make sure that every point of your architecture is being done in a resilient and distributed way. So here, if I wanted to create an endpoint, I could do any number of these sizes. I could have it stop automatically after 10 minutes. So if nobody runs any queries for 10 minutes, it'll just shut down all the infrastructure. I can set it up so it's automatically scaling, so any number of clusters that we need. And then, this serverless allows you to basically have instant access to compute. So like how serverless works for, all the vendors that do this is they have some bank of machines that are always up and running. And then when a customer needs some of those machines, they have a very easy, quick way to grab some of those machines, deploy whatever containers and code they need onto it, and then make it available behind the endpoint. Because the slowest part of spinning up any infrastructure is basically asking the cloud provider for the virtual machine. So if you can already have a bank of those up and running, then you can have easy access to the clusters. All right, so this is my final section before I hand it over to Sean. But governance requirements for data are quickly evolving. So we talked about how data lakes basically were born on working with files and folders of files, and then data warehouses were born working with tables and structured data. So you've got those two different paradigms. So data governance, it's hard enough to enforce on the data lakes, especially if you've got structured, unstructured, and streaming data. And then you might be doing this across multiple clouds, and you've got different users that have to be downstream of this. So, and the problem is getting bigger because you need a way to share and govern these data products. I talked about how the term data product is getting used a lot now. It kind of means like any sort of output that your data team generates to help with their end users. That could be a dashboard. It could be just a table of data. It could be a machine learning model or a dashboard. So all these different things need to be governed, and they're being governed in different ways all the time across different systems. So with the Lakehouse, we want to reinvent how we can do governance on these things. So you have one common way using ANSI SQL API to be able to govern files, tables, but also your machine learning models and dashboards. So data governance on the Lakehouse, how does that work basically? So we've created this thing called Unity Catalog as an open way to do Lakehouse governance. It basically provides a way to centrally catalog, search, and discover. So we focused on, as you're building out your data engineering pipeline, your live table pipeline, if you can embed like the comments, the documentation in your comments, you can then search for that stuff later on and easily discover it. We want to have a single governance model you can use across all your clouds. So we're standardizing on ANSI SQL. So there's been the domain control language part of the standard for a number of years. If you want to grant access to a group of users, you could say grant access to this table to this group. So we're standardizing on that. And the great thing about that infrastructure is that there's already so many different systems that have out there that have been built to generate that type of SQL. It'll be very easy to plug into it. And today, you might just be granting access to a table, but you could just as easily grant access to a location where you've got a bunch of files, or a dashboard or a machine learning model. These are just different object types that can be created in the Unity Catalog layer. And you want to be able to securely share your data across the platforms as well with Delta sharing, which I'm going to go into for a little bit. So data sharing, it's becoming critical in the digital economy. There's historically, like a lot of companies have been sharing data, but the way that they do it is typically generate some sort of like CSV file or a fixed width file, and then FTP that to your customer, partner, or supplier. And then it's up to them to take that file and then do their own ETL on it, adhering to some sort of spec that might be like a 700-page PDF file, and then basically keep that ETL in sync with the spec as they change and iterate through new versions. So there's just a lot of redundant work that's being done across these pipelines anytime somebody wants to share data. So we think there's a better way. And the companies who can, figure out how to be effective at sharing their data, essentially they'll be effective at monetizing their data. And this is going to be one of the key ways that companies make money, in the future. So I think it was Allstate that created this subdivision called Arity Insurance. And what they did is they recognized that the amount of premium you can get for personal auto is going to be going down over time. And so they were looking at how can they monetize their data. So they've got a lot of telematics devices that they've been using with their customers, and they're capturing a bunch of that data. Can they take that data, anonymize it, and then monetize it in a way that produces a stream of revenue that's over and above what they were getting from the direct written premium? So this is something that companies around the world are figuring out right now. So the current options that people are using are basically not fit for purpose. They're homegrown solutions. I talked about FTPing these flat files, but they're not scalable. It's complex. It's brittle. And then you end up like having to do these point-to-point solutions all over the place. And then there's commercial solutions that have been out there for a long time. A lot of data warehouses have had ways to share data, but it's expensive. You get locked in, and it's inflexible. And it's sometimes difficult because if you're sharing data from your data warehouse to one of your customers who use a completely different data warehouse, now, what do? Either your customer would have to like adopt the data warehouse that you're using, but then they would have to go through some long, purchasing cycle to do that. Or you end up just sending files in FTP, and now they got to do this ETL. So this is pretty much how people have been doing it for decades. It's not that people have not been sharing data. It's just that it's been very painful to do so. So we want to take an open approach to sharing. Last year, we announced a new open source project called Delta Sharing. And it's fully open. It doesn't have any proprietary lock-in, and it allows you to share data from your existing Delta Lake with other people so they can easily query it. And it's done in a way so it can be secure, and you can basically make sure that you're only sharing data with the recipient that you intend to. And because it's an open standard, it's going to encourage lots of other vendors and people to adopt it. But it's already being integrated into key open source frameworks out there. So what happens is, let's say you've built this lakehouse, and you've got Delta Lake as the foundation for that lakehouse, and you want to share some data with someone who's in another company, another organization. What you would do is create what's called a data recipient. So a recipient that conforms to who that other organization is. And then you're going to use this Delta sharing protocol to do that. So what happens is you create like a Delta Lake table, and you want to share it with someone over here. So you create a recipient. They get a one-time token. So they get access to a website where you get one chance to download this token and register that as yourself. And then you can use that to access the share, which is basically a collection of tables. And then you can basically query those tables. So we've already got partnerships. We've already got clients for Delta sharing built into Pandas, which is on Python, Apache Spark, as well as Java. But we've got commercial vendors that are adopting this as well. So Power BI and Tableau. And what happens is in Power BI, you can basically point to your Delta share and say, I want to query this data. And it'll actually figure out what files in object storage it should ingest to satisfy that query, and then do it directly into Power BI. And because your Delta Lake is on cloud storage, and cloud storage is, on these cloud providers that are already scaling around the world, it doesn't really matter where your data recipient is. They can easily query this data. And so this is the power of it. And then the recipient, they don't have to do any sort of complex ETL. They don't have to, manage an FTP server anymore. It just makes things that much simpler. So we believe this is going to be, it's really the first true open standard for this Delta sharing or for data sharing. And it's getting adopted more and more by different vendors. And I think it's going to be just the common way that people share data across their lake houses. All right, so I think that's pretty much everything I have for the first part of this. I'm going to turn it over to Sean Owen, but before I do, I don't know if we want to take a 5-minute break, and then I'm going to basically go into the comments and questions and see if there's anything that I can answer. So if that sounds good to everybody, let's see. Do you want to return at 10:20 Pacific time? So I guess that'd be 11:20 Mountain time.
Yeah, sounds good. Let's take a break. Jason, I tried to answer the questions. Probably got half of them right. Just don't know which half. But maybe take a look and add some color.
All right. I can.
While we're taking a break, maybe we could even casually discuss some of the questions that came up as an ad hoc panel here, as people are getting a drink of water.
Were there any common ones that kind of came up?
Yeah, let me go back and review here. One comment, which I think I'll try and get to here is AI the use case for the Lakehouse? I think it's probably one of a big class of use cases where the premise here makes a lot of sense because you're going to need to do a lot of different things, not that maybe beyond what data warehouses are good at, beyond what a simple data lake is good at. And so trying to do both at once, which is harder, can be nevertheless important for that class of use case. And we'll definitely get into that in 5 minutes here.
Let's see.
A number of questions about lineage, governance. Also, can you use third-party tools like Calibra with this? And a lot of what you described are like elemental pieces. Like I need to manage my storage, I need to secure it, I need to version it. But if I want to do things like figure out who ran this job, what time, what does the Lakehouse architecture offer? Is that fundamental to the Lakehouse architecture? Maybe in the specific case of Databricks, since we're here, what do people do for that kind of thing?
Yeah, I mean, so I work with a lot of customers, and it's very common to have enterprise data catalogs like Calibra or Informatica or Elation. And typically they've been established because they're trying to get a holistic view of all their data across their enterprise. So it's, they've been basically connecting multiple data warehouses, multiple data lakes, but also, operational databases, maybe ODSs. So there's all these different systems that they're integrating to. And I think, I don't see all of those systems going away overnight or anything like that. So there's going to be a need for enterprise data catalog to ingest the metadata and the lineage from the Lakehouse as well as the other systems and have a centralized place to govern that. There's also like some of these catalogs, maybe not all of them, do like the whole entitlement management process where, somebody requests access to data, it has to go to someone to get approved, and then after approved, the access gets granted on that data and eventually it gets audited. So in that scenario, you need some sort of workflow to manage that. Some of these data catalogs do that as well. We just need to make sure that, for the Lakehouse, when it comes to granting access, there's an easy API-driven way, like with ANSI SQL, domain control language statements, to be able to grant that access, and if need be, revoke that access as well. Let's see. Does Data Lakehouse require to move data from data warehouse and data lake? I mean, I think I don't know at what point this came in, but one of the points I was trying to make was that we've had like this architecture for a long time where you've got a data lake and a data warehouse. The data lake basically is the staging ground for all the data, and then a subset of that data gets aggregated and pushed to the data warehouse. But the Lakehouse now is this pivot point where you can essentially run all the same queries that you were running on your data warehouse on top of your data lake. And it's because you have this foundational layer of Delta Lake to provide these ACID transactions. And so you can essentially run all the same use cases that you were on the data warehouse on top of your Lakehouse. So you don't have to copy the data anymore, and you don't have to keep those two copies in sync.
Obviously we're here talking about Delta. Delta is an open source project from Databricks. We're Databricks, but we'll obviously want to talk about the concepts more broadly as well. And a couple of people brought up other interesting open source projects, Hoodie, Iceberg. I think it's fair to say those are a project with similar design goals to Delta. And I don't know if we would get into pros and cons or contrasting, but yeah, it's not just Databricks, not just Delta. This is a common pattern that you see a lot of open source projects springing up to help solve. The Lakehouse is certainly underpinned by projects like this that enable data warehouse-like operations on data lake-like storage in the cloud. So there, you have options here. We're definitely talking about Databricks, but a lot of these ideas would transcend Databricks or Delta.
Yeah, I think there's just recently, I think this week, there was a company that was announced behind Apache Hoodie, and then Iceberg has a commercial entity as well. And between Apache Iceberg, Apache Hoodie, and Delta Lake, which is under the Linux Foundation, you basically got these three common ways to do it. And I think the cloud vendors themselves are supporting all these different formats. So if you were to just think if you were to build a data lake today, would you use is it more likely you would use one of these layers, or is it more likely you would just continue writing raw files out to your data lake? I think the trend is that everyone is moving towards these Lakehouse layers, and so you could definitely go and compare and contrast and figure out which one makes the most sense for you. But hopefully you give Delta Lake a good shot as well.
Maybe we can take one more question live here, the latest one. The Delta's Parquet formatted storage is just an analytical infrastructure, as mentioned in the ebook. Would you describe Parquet as the analytical infrastructure here?
The Parquet is the analytical infrastructure. Parquet is
it's the storage, right? The infrastructure is really compute on top too, right?
Yeah, Parquet is just a file format. So when you go to, if you export data from Excel and you save it as a CSV file, that's a text format. If you save it to Parquet, it's a binary format, but it's because it's open, it's this common accepted binary format that almost every tool knows how to read now. So you can take the same amount of data and save it in a much smaller footprint, less megabytes. And you can, when you go to read it, you can, choose to read only certain columns out of it because it's a columnar format. Whereas with a CSV file, you'd have to read the entire file and then filter it down from there. So it's got a lot of performance characteristics, but it's also good because it's a binary typed format, you can save things like strings and integers in specific formats in specific ways.
Cool. I'm guessing people are filing back in. We're at 20 past. Maybe I can take over here and take us home with the final section on machine learning and data science. Let me go back to the slides here. Give me 1 minute to figure that one out. Window. Okay. Hopefully we are looking at slides again where we left off here. Number 5, machine learning on the Lakehouse. Present here. So as we talked about briefly in our discussion, indeed, one of the big motivating use cases for the Lakehouse architecture is machine learning, which is a big category of use cases. If you're not doing machine learning now, you probably want to, or you will soon. And it's useful to unpack why that is. Maybe not why is machine learning interesting. I think we all get that now, but what does it really need from our data architecture and our infrastructure? And why is the Lakehouse idea a good fit for that? So why is it maybe not a perfect fit for the data warehouse or the data lake itself per se? So, I think if you look at our diagram here, what we try to do at Databricks specifically, but indeed a lot of companies, you'll see data science and ML. It's a first-class citizen these days. It's a first-class goal for a platform that's there to store data, manage compute, and so on. So we have to pay attention to it. We have to cater to this type of use case, or we're trying to. We're not just there to help you crunch data or expose it to a BI tool. We want to enable the world of data science and machine learning, of course. And so, as you'll see in our stack and most people's stack, data science is in there. And it's not just one box. It's there's a lot of pieces to doing data science. It's surprisingly complicated in its needs and the tooling required compared to maybe a simple SQL workload. Thankfully, we long ago standardized SQL, and that's served us well as a nice standard interface to data. Machine learning has no such standard, as you'll find. In a way, it shares a lot more attributes with software development life cycles than maybe data management life cycles. There's a life cycle to doing data science. We're going to build models, but we need to track them and promote them. We need to monitor them. We need to govern the whole process. Now, here I'm not necessarily going to talk about the problem of ML ops specifically. I want to keep this grounded in the lakehouse. Why is this life cycle? Why does it have specific needs, different needs than maybe you might be able to support in a data warehouse or a data lake separately? Like, why are people bothering? Why is there a new thing suddenly? Didn't we go through this all again before with Hadoop? For me, I like to start by thinking through the actual end users that we're trying to serve with our data infrastructure. What people are doing things you might call analytics or data science. And in my head, it might break down three ways. There's three distinct audiences. You may disagree, but this is maybe a useful approximation. Number one set of data users are the business intelligence users, the BI users. They are definitely using SQL. They are using BI tools, almost surely. And they are running reports. They are generally summarizing data. What happened? Let's run some aggregations, maybe visualizing it as well. And this is a very useful meat and potatoes analytics. That's important. Sometimes this occurs on big data sets too, sometimes. And they're typically, this audience is accustomed to working out of a data warehouse. Data warehouse is a good tool for this type of use case. In fact, in a way, because the data warehouse tends to be able to assume and focus on this relatively simple and standard API, user surface, SQL, it can do a lot behind the scenes to optimize storage and queries and so on. And that's why data warehouses have been successful and remain useful as an idea. But as we go to the right, maybe the users are less and less suited by a data warehouse. So there is the conventional data science user. I'll say they're the people that are more likely to use R and SAS, statistical environments, than maybe Python, but maybe Python. They're doing what we might more readily call statistics. They're explaining data, also visualizing it, building models in some sense, but building statistical models. And this has been going on for a long time. This is nothing new. Often the work of traditional data science occurs on smallish data sets. And sometimes some of this tooling pulls data from a data warehouse. As often though, the tool sets here don't assume data warehouses. Tools like R are the kind of thing you run on your laptop. They're used to working on local files. They are used to enabling things that aren't just data aggregations that data warehouses might readily support. And so they have slightly different needs. We're not just in SQL anymore. We might need more generic access to data to use these tools. And I think that gets even more true when we think about the machine learning user. Machine learning is relatively newer, I would say. Depends on how you define it, I suppose. But I would say machine learning concerns building predictive models. That's the thing. Trying to learn from past data to predict something that's going to happen in the future. The key language for machine learning is Python. Almost all of the tools people use are in Python, and they're open source tools. Often these workloads are big. need specialized hardware like GPUs. That's GPU prices are through the roof in part. Sometimes the machine learning occurs on big data sets, sometimes not. But more than in the other cases, machine learning often occurs these days on unstructured data. Because we've been so good historically at managing structured data, a lot of the tooling and focus has been on working with structured data. If I have good measurements of the weather and foot traffic in my stores, and I have good measures of sales, well, yeah, I can probably predict those. But the question, things that have become possible in the last 5 to 10 years are fairly different. Maybe I can take pictures of people in my store. Maybe that's a little bit creepy. Pictures of the parking lot in my store and work out footfall. Maybe I could take transcripts from my call center and learn something about what users are saying when they call us. Those are more complicated problems that definitely don't fit the structure paradigm, don't necessarily fit the neatly into gold tables that we might pull from a data warehouse. And you'll find indeed a lot of these tools people are picking up that you've heard of: Keras, TensorFlow, PyTorch, scikit-learn, XGBoost. These things don't really necessarily assume tables or SQL or anything like that. They're much more readily assuming files. I'm going to learn off a set of images. So all these users are important, and I think that not the data warehouse by itself or the data lake by itself don't necessarily cater to all of these users simultaneously, because as you can see, these are pretty different needs. So I'm going to focus a little more on the machine learning user here in the rest of this 45-minute session or so. But of course, we need to cater to all of them. And I guess I might put these on a spectrum. I think that BI users are pretty well served by data warehouses. That's obvious. You all are doing that today, and that doesn't really change. Machine learning users, on the other hand, are probably not, just because they are not working in SQL. They're not necessarily working on structured data. They need exotic hardware. They need arbitrary open source libraries. Sometimes they just have to write code. And the data lake architecture feels like it should be good for that. The data lake, and my crude summary is the data lake is about files, not tables. So that sounds closer. I do think the data lake idea was to be more simplistic. Let's not assume a workload. Let's not assume we're going to act as a data warehouse. Let's just provide a substrate for storing stuff and running some arbitrary compute, and the rest is up to you to manage, which made it in some ways harder to use because you had to build out a lot of applications on top of that. You had to go figure out security again, figure out SQL again. But for workloads like machine learning, that was kind of okay, because to begin with, they wanted to do arbitrary things with code, to arbitrary data as files. So that simplicity also offered flexibility that was attractive. And that's why I think there was some noise about Hadoop. Noise was made about Hadoop as a good platform for scale-out machine learning. That's certainly where I got my start 10 years ago, trying to build out scale-out machine learning on things like Hadoop. But in the end, we'd rather cater to all of these audiences in one place. We'd rather not have 2 or 3 different environments. And increasingly, these not just these disciplines, but their supporting disciplines like data engineering are kind of coming together in a lot of ways. And it'd be painful and expensive to continue to operate 2 totally different worlds just to be able to do BI on the one hand and maybe machine learning on the other. So the premise, I think, of the Lakehouse is maybe naively, can't we just do both? Why can't we just do both at once? And I think the answer is with work and advances in technology, yeah, you can get most of the effects of both. So let's stop talking about warehouses versus lakes and just go with the lake house. And that ultimately is good for machine learning because machine learning does need a lot of flexibility and expressiveness, but at times can benefit from some of the paradigms, the styles of interaction that might characterize business intelligence or data science. So it's going to be a win for all of these users if we can kind of merge these ideas. So what does machine learning need from a lakehouse, but maybe in general? What does machine learning need? What are its concerns that are maybe a little bit different? Well, as I said, generally, Well, machine learning could operate on structured or unstructured data, but these days, I think a lot of the attention is on the unstructured data. It's not that structured data has gone away. It's not that simple, traditional supervised machine learning is less important. It's that we already kind of know how to do that. It's already fairly well established how you can take structured data and learn from it. The frontier, the untapped value, may be in the unstructured data you also have. So not just in someone's summary of a chat transcript, yes, the customer is happy or not, but the actual chat transcript, for example. As we'll see in an example, I'll show you images. Maybe if we aren't just recording what doctors diagnosed about a patient, but actually showing the x-rays and learning how the x-rays led to that diagnosis, maybe we can open up some interesting augmentation and automation possibilities. Machine learning doesn't have to necessarily take place on massive data sets, but generally, the more data, the better. Machine learning is about learning from data, and the more we can learn from, the better we can learn about the reality that generated the data. So that is certainly part of what drove the initial push to the data lake, things like Hadoop. The promise was, well, at least it's cheap, so that now it becomes economically feasible to store and do something with massive amounts of data sets. And that turned a lot of the attention in research to taking advantage of more data sets, not just working out how to make do better with a sample. So that possibility has driven more interest in learning from all data, not just what I can manage to break off and fit into my statistical environment. So any architecture that supports modern machine learning probably has to have a scale out story. It probably has to be able to consume unstructured data and at scale and do something with it. I think that's a given. One clear attribute of machine learning, I think, is how much it's dominated by open source tooling. And I think it'll be obvious for anyone that's in the space, but if you do data science today, you are using tools like Pandas, NumPy, scikit-learn, XGBoost. All of these are open source projects, freely available, and they are the state of the art. They are cutting edge. When we talk about all the advances in deep learning, those models are generally available for download and use with tools like PyTorch, TensorFlow, Keras. So you have to be able to accommodate this. You can't really have a platform that says, yeah, that's great and all. This paper just came out from Google. They've done some really breakthrough research. They've made their work available, but you can't run that on your data. We have no way to use that, even though it's someone's handing it to you. So it's, I think, absolutely required that a platform support open source tooling. These open source tools tend to, although SQL's in here, I think SQL is usable with a lot of open source tools. The much more common paradigm people work in are data frames, really abstractions of tabular data in programming languages. And this is true in Spark, it's true in Pandas, it's true in just about any framework. So we need to support those paradigms, those types of tools, because that's how the ML users are going to be accustomed to working. They are used to tables. They are not necessarily used to going entirely through SQL. The outputs of machine learning are also somewhat different, possibly, than the outputs of an ETL job or even some statistical analysis in R. Sometimes those the output of a BI tool and data warehouse is a report. Likewise, the output of work done in R is maybe visualizations. Typically, machine learning is synonymous with making predictive models, and those models need to predict. They are artifacts, they are functions that need to be applied to data to create some answers. And that is the primary output, something that works more like a software artifact than more data or a report. And last but not least, I think we'll find that some machine learning, certainly the machine learning that's getting a lot of attention these days, deep learning, is it has extreme compute needs, let's say. Some of the latest language models people are running have billions of parameters, hundreds of billions. And they take literally days and days in a data center powered by enough power to power a small city. And the only way this even begins to scale is through specialized hardware. We're talking about things like GPUs that are commonly deployed to help scale up these machine learning modeling tools. So we're going to need some story there too. If we want to do deep learning, you're going to need access to specialized hardware at times. And thankfully, a lot of that hardware is available in the cloud to rent by the hour. So I think this also suggests that maybe for machine learning, cloud elasticity is maybe even more important. We're going to run some heavy compute workloads that need some pricey hardware, but we may just need to do that for an hour every night or every week or something like that. So we're going to need a story here too. It's a lot to accommodate, I think. Doing all of these things at once, providing open source libraries, optional access to specialized hardware, access to unstructured data, and then putting some life cycle around that too. It's it's a lot to ask here, and I think that if you try and think about the traditional data warehouse, it's just not built for this type of workload. It's specialized for a very important and still important class of workload, but it's not this. Think about things like images. How would I store images in a data warehouse? I could probably put them into a binary column. But is that going to be an efficient way of storing the data? Maybe, maybe not. I have to ingest it into my data warehouse rather than just stick it on cheap cloud storage, which might work. I'd have to pull it back out through SQL. And meanwhile, all these open source libraries I'm probably throwing at it aren't expecting that in a table. They're expecting to read files, raw files. Generally speaking, data warehouses don't really provide access to data in other languages. Some exceptions, typically they exist outside the data warehouse. You can pull your data out and do something with it in another language. A little harder to do it in place in the data warehouse. And often no real attention to supporting software artifacts or model artifacts. Those are maybe somehow incorporatable through UDFs, but not often a first-class citizen there. And specialized hardware, one of the upsides of data warehousing is that they can often manage compute and infrastructure for you under the hood and make you not care about that and let the data warehouse optimize it. But here, unfortunately, you probably want access to the hardware because your libraries want access to the hardware. And you don't just need CPUs, you need very particular hardware as well. Even the data lake, I don't know if it necessarily fits this that well either. Data lakes tend to be very much DIY. Yes, they're a good place to store files. They're a good place to run compute, but they don't really do much beyond that to help you manage your libraries, for example. They don't necessarily have much concept of models as a first-class citizen. So it's the data lake is maybe too simplistic, too broad, too flexible to really effectively support these now common workloads in machine learning. So the lakehouse, as before, as now, I think the idea is, can we do both and get the best of both worlds for this, this type of workload? Sometimes people have asked, how is this different architecturally? I tried to draw a picture here. And if you recognize this is from chapter 5 of Bill's book, which I contributed to. So this is a lot of the ground I'm covering here is in that chapter as well. In a traditional data warehouse, I think it's fairly simple in a way. The data warehouse is effectively a SQL engine on top of proprietary storage, and everything connects through that SQL engine. BI tools do. Third-party languages for doing stats, things like R, just connect through the SQL engine, and that's nice. But it's in a way that's can also turn constraining as well. So in a lakehouse, the picture is more complicated because it's trying to offer more possibilities as well. On the bottom of the right side, you can see, again, one of the key architectural attributes of lakehouses you'll find is open storage, and probably in the cloud. Now, I don't think the lakehouse idea is necessarily specific to the cloud, but you would almost always see the lakehouse deployed in the cloud. That's the direction of things these days. And probably because people want to get these workloads in a place where they could conceivably share data, share compute across applications. So if you're going to be in the cloud, probably one of your premises is because I want other things in the cloud to be able to work with my stuff. So it makes more sense to adopt open storage at the storage layer and maybe just operate generally on standard representations of things like text and images as well. So under the hood, instead of having closed storage, which the data warehouse kindly optimizes for you, you have open storage in the cloud that nevertheless can probably achieve some of the same goals as a data warehouse. It's still possible through open formats like Parquet, engines like Delta, to achieve speed and management and security on the same data without actually requiring the whole piece to be a black box. Then the user space possibilities open up. Yes, you can have a SQL engine on top of this data, but you can also run Python applications on top of this data too. That doesn't necessarily need to go through SQL engine to access structured data. BI applications could, R applications could, but they could also go straight to the source data as and when needed. Go straight to the image format, image files on distributed storage, and then build on from there. Applications could then go through these libraries to do their work. So more moving pieces, but probably because there's more possibilities here as well. The Lakehouse is trying to do more. It's trying to also subsume things that might only otherwise be possible in a data lake. One of the final big classes of needs that I think you'll hear a lot about today is ML ops, ML operations. Just like we have DevOps, just like we have data ops, we have ML ops. Now, ops is it's an operational set of concerns, but nonetheless quite important. When you're thinking about how an architecture might support ML, you have to think about how it's going to support all the operations around ML. The goal is not just to expose data, run compute, but do something useful with the models as a result. So I think that MLOps is a key question that's intertwined with the question of whether to adopt something like a lakehouse architecture. So as I'll show you in the demo, there's, again, more open source tooling that is intended to help start to answer these questions. Got a lakehouse, I got my data. I've built a model, and that's good because I can apply a bunch of libraries at scale to my data, whether it's raw data, whether it's tables. But then I need to do something with them. I need to apply the models as well. How do I do that? How do I apply that to data at scale without, again, moving to a totally different environment? Models in a lot of ways act like data. They are sometimes shared across environments. Sometimes there's a promotion process. In some ways, they act like code as well. And there are concerns about security and governance. Where did the model come from? What data was the model fit on? And how do I expose this model as a service to other tools? In much the same way you might ask, how can I expose my data to consumers like BI tools? So these same sorts of concerns come back in slightly different ways, and we need answers to them. And that's, I think, where the open part of the lakehouse, the lake end of it, does help and does shine here. Now, to maybe make this a little more concrete, I'd like to walk through a representative example. I'm going to show it to you in Databricks, though I think the ideas are not specific to Databricks. Certainly, I'm just going to be using open source tooling here. And the example will concern chest x-rays. So imagine we have a bunch of x-rays, patients where something's wrong. And doctors have diagnosed the patient, so they know what's wrong given the x-ray, a professional radiologist. But we're interested in doing more than just storing the x-rays, storing the diagnosis. We want to learn from it. We want to learn what about the image maybe caused the doctor or radiologist to diagnose it as one thing versus another. This is an interesting open data set I'm going to use here from the National Institute of Health. And by the way, we're happy to share this notebook afterwards if it's of interest. Now, the cool thing is This these days is an easy problem to solve, relatively easy. I mean, even I got a pretty good result out just doing the simple stuff, applying open source tools, reusing existing models, scaling out training. That it doesn't have to be hard if you can access all those ingredients. So it would be impossible if I didn't have the data, or I had the data but I couldn't get to it, or I didn't have tooling, or I had to build the tooling. It would be slow if I didn't have GPU hardware. But if I have all those things, and then this is actually quite easy these days. Even I can do it. The results I'll show you, of course, are just an example. Please don't try and diagnose chest X-rays at home. It's just a representative example of what sounds hard, but is not hard these days if you can pull in all the pieces. And I think that's where some of the things we've repeatedly mentioned as the value proposition of the Lakehouse really shine. I can work with unstructured data and structured data and combine it, and at the same time go off-road and pull in open source to build the model. I can still come back and apply the model to data in tables as well. And this line between lake and warehouse kind of starts to blur and go away. In my process, I use the tooling that I need. It makes most sense, and rather than have to adapt to the tooling I've got or move back and forth across environments. So if you want an architectural picture of what's going on here, we're going to start with data in the cloud, a bunch of images, and also their labels, which are also just a bunch of data files. We'll treat them as tables as is. We're not even going to have to ETL them, really. And we're going to ultimately apply deep learning libraries to learn from the images. Those are going to take advantage of specialized accelerators in the cloud, like GPUs, to speed that up. And then we're going to use some open source libraries to manage the artifacts that come out of here, the model, and ultimately see how we can even expose that model. And this is so that our application is really a notebook that sits on top of that, all running in the cloud. So with that, let's take a look. Let me switch over and show you what that might look like here. So again, here's Databricks. The paradigm here is as you've seen, notebook-like, which is nice because that's the default paradigm for data science. I write code, I execute it interactively. And a couple elements pop out here that underscore, I think, some of the advantages I'm promoting here. Number one, easy access to open source. So in Databricks specifically, but in a lot of tools, you'll find the compute environment is set up for you. So that's no different in Databricks. I can just attach to a cluster of compute in the cloud. It even has a bunch of my libraries already installed. But if I want to use the latest and greatest piece of software from Facebook, for example, PyTorch Lightning, I can just install it and use it because I'm here just writing Python code. It sounds simple, but it's pretty powerful. I mean, there's no more steps. There's no more integration. I don't have to wait for my data platform or compute platform to support this. I just install and go. The data engineering piece of this is a little bit interesting. As I say, we start with data in the cloud, a bunch of images. And in the Lakehouse paradigm here through Spark, in a way, doesn't have to be a lot of difference between unstructured and structured data. So here I'm asking Spark in particular to read a bunch of files, a bunch of images, and it's happy to return that as a table, really. It's a data frame, a tabular representation of all the data about those images, the image, and some metadata, path and so on. Storage here is actually just I'm in Amazon AWS here, so this is actually just an S3 bucket I'm loading from. And in the Lakehouse, we actually make those look like local files even. So software you want to run that is built for people running on laptops, that's assuming a local file system, that still works here too. So I've read images, I've read unstructured data in a sort of structured way, and that's no problem. That's just as easy as breathing in the Lakehouse. It's a very natural thing to do. But there's a little more to it. So I'm going to need to transform these images. They're not all quite the same. They're not all quite the same size. Some of them are in different formats. Some of them have multiple channels. I need to standardize them. The normal thing I might do to get from bronze to silver, something like that. And that might be hard to write in SQL. I don't know the SQL command to normalize images. Sometimes SQL data warehouses do have specialized libraries for this, but I definitely know Python has libraries for this. I definitely know the 3 lines of code that will do what I want here. And again, that's not hard. If I want to just write some Python code and apply that to data, to my table of images, I can do that here. So the mixing and matching of unstructured and structured data paradigms, mixing SQL and mixing Python, very common sort of thing. And that is beneficial. I can just at every step here, even within a notebook, choose what makes most sense to do. There's a little more data out here, the labels, the actual findings. And it lands, I think, in this data set as a CSV file. And I'm not even going to bother to ETL this or put it into a table, because I can read anything like a CSV file as if it's a table here. I've got it, it looks like this. This is the data inside it. And I just need to do a join here. So again, with a little massaging, which is probably easier to say in Python than SQL, I can do that and ultimately get a table out with image data and the labels, because that's what I need for my deep learning. And I'm going to go ahead and write that out as a table here. Same sort of thing you saw in Jason's example, because it probably is useful to manage this handoff from the data engineering to the data science as a concrete table, as a delta table, in fact. That buys me a few things. Among them, well, the ability to ACL it, of course, but also time travel. As I ETL images and more arrive and the data set changes, I can't always go back and query the previous state of this delta table. See what the data and images look like last week, maybe before someone changed a label because they thought they were fixing it. Things like that become, you get for free here. So we kind of come back to a tabular representation, having started from unstructured data and plus some structured data in a open format, just because it seems like the natural thing to do. We can weave back and forth. I'm not going to go into the deep learning code here. It uses a tool called PyTorch. Suffice to say, this is all just standard code that you might pick off the internet, that your recent graduates that are trying to do data science will have learned probably in their classes. All this stuff, in Databricks in particular, but in the Lakehouse in general, is possible to execute, because paradigm here is we're happy to execute code as well and execute it at scale, but there's not necessarily a new or different way to do this. You don't have to go through SQL. You don't have to do that. You can just execute your code. Another, and I won't run this in real time. It does still take probably an hour to train. But what you don't really see here is that this also took advantage of a GPU. Last time it was run, and it turns out in the cloud that sort of thing is quite easy. At the time I just called up a GPU, which is nice. So I don't have to buy the GPUs. I don't have to pay for them when I'm not using them. I can just say, you know what, today I need a machine with a GPU here. Let me pick our latest GPU runtime, and I can rent this by the hour. Again, we're looking at Databricks here, but I think you'd find this is a property of lots of cloud lakehouses, easy access to compute here. And the nice thing is from here, what I do with the model is also pretty flexible. I think you'll find that because the Lakehouse is open, and it makes it possible to integrate open source packaging. We can integrate open source tooling to help support the modeling lifecycle. And one key piece of technology, it's from Databricks, but it's not specific to Databricks. It's open source. It's called MLflow. This is a tracking and deployment system for models. And that will come back and be relevant to I think, the Lakehouse architecture. One nice thing MLflow does is tracker models. So as I built the model here, I got a nice some tracking here. This is what it logged. I got the model and its necessary environment, who did this when, running what code. So there's some lineage here, support for things like lineage and audit for the modeling parts too, not just the data transformations. But the nice thing is, if I've got that model, I can do a bunch of things with it. Number one, I can deploy the model as a service. which is sometimes the right thing you need to do. And I don't think I'm going to go into this too much, but tooling like MLflow, like Databricks in a lakehouse architecture tends to have a lot more sophisticated support for not just storing models, but applying them, even turning them on as a real-time service. And I can permission that to control who can put things into production and even turn on inference for it. Maybe the more interesting thing you can do, though, is turn around, take this model and apply it to data as a UDF. And I think in this example, I'm not sure I actually show it. Maybe, shoot. But you could take this model and load it back directly as a UDF that you could apply then with Spark or Spark SQL to apply that model to a bunch of data with just a couple lines of code or SQL as well. So models managed as functions in the Lakehouse become useful because those functions can be SQL functions. They can be Spark functions that are just applied to tables of data in batch or in streaming as well. Here I'm actually showing an example of classified an image, but this is actually going to the API, REST API. And we can do more fun stuff too, which is, again, not really specific to the Lakehouse, but an example of the possibilities that open up if you can just throw any old cool open source tooling at your problem. For example, maybe I want to explain the model. Why did the model make the predictions it made? Normally you'd be out of luck if you had to rely only on software you could get through your warehouse or something like that, or you had to pull it to a different environment. Might be a lot of work. Here, I just install a cool package for this called SHAP and just throw it at my data. Yeah, it's a little bit of code here, but I get some interesting results out. Here's an image. Here is why the model classified what it did. It seems to be looking at something here, this little black area on the left lung here. I'm not a doctor. I don't know if that's valid or not, but this seems to be germane to its diagnosis. And this kind of thing is easy with open source tooling, but the only hard part maybe is I've been able to apply that open source tooling. And if I can, lots of possibilities for machine learning open up here. You can see how this could easily lead to a pretty short job of running in my Lakehouse that takes in images and even forwards the doctor its own preliminary analysis of the image. Doctor, what's wrong here? By the way, the model calls your attention to this point. And because we were able to throw open source to this, throw compute at it, get the right hardware, this can be, an afternoon's work and half a page of code, and that this use case is enabled. I want to come back briefly to, I think, one last topic that may be of interest here as we're talking about Lakehouse, data management and data science. Obviously, data is important to data science. Data is important to machine learning. Can't learn from data if you don't have data. And actually, what I've emphasized here so far is model management. Yes, that's an interesting and unique output of the modeling process that needs its own attention, but the data needs attention too in the modeling process. We've heard that things like Delta can help you store your data and offer transactional updates and time travel and so on. Sometimes machine learning needs a little bit more than that, than just data in tables. And that's where something called feature stores come in. You may have heard of feature stores. Sorry, slideshow. Feature stores, I'm wondering what these are. Is it a different type of system? Where do I buy it? Can my data warehouse do this? I think there's maybe less to feature stores than meets the eye, but it's worth explaining the problem they're trying to solve. And then I can briefly show you how that might manifest in the Lakehouse and something like Databricks. I think one of the problems you find in data science is reuse. So team one takes some raw data, has some success building some model. They build data pipelines. They're building nice gold tables of aggregates to feed their model, and they're successful. Team two comes along. They're going to build a different model on the same data, and they might look over and notice that team one has done some interesting work that's relevant, but maybe they're hesitant to just go reuse some of the data in those gold tables, because how do they know if team one is going to change that table and drop the column? How do they know if they're not going to change the definition tomorrow? How do they know how often that data is updated? may have trouble even figuring out how it was computed. So they probably go off and build their own pipeline. They maybe do some of the same work. Maybe they get the same answer for the same question, who knows? But you end up with some duplication here. And what you'd like instead is to support some degree of discovery of features. I'm working on a customer churn problem. Who else has worked on customer-related modeling problems before and maybe computed some interesting stats about customers that I might use in my model? We also probably need some lineage here, not just for audit purposes, but to help reusers understand how the features were computed. I may see that one team has computed customer lifetime value, but how did they do that? Do I agree with it? Is that computation relevant to the way I want to compute it for my model? So we'd like to have lineage for the purpose of letting other data scientists go back and see how things were computed, maybe fix them, maybe improve them, maybe reuse them. The more interesting problem, though, comes when you actually use the models. And this is the important payoff and punchline to managing models to begin with in the Lakehouse. Yeah, we want to apply those models maybe in the Lakehouse architecture. But the thing is, there was some feature engineering that had to happen before we could use that model. We took raw data from our unstructured sources and from our tables and joined it and transformed it. But we're going to need to do that again to new data that's arriving. And the team and the pipeline managing that may be separate. And they're going to have to figure out how to apply exactly the same transformations to new raw data to get new features to feed into a model to even use it. That is a big pain point. That is probably not unfamiliar to many of you used to managing data, where perhaps different sources need to be transformed in similar ways, and you're trying to keep those in sync. But that problem definitely comes up directly in machine learning, because you will definitely be transforming more new data to apply your model to. If you're lucky, we'll do all this in one place, like the Lakehouse. I could maybe reuse the same transformations. Maybe that's a similar job, but that's not often the case, or not always the case. Sometimes you're in the same platform, but some other team's running the job that does the inference on the model. And so now you're trying to make sure y'all are running the same transformations, sharing code. Possible. If you're unlucky, though, maybe some other team entirely, some other system is feeding the request to the model. And you are then thinking about how to reproduce all those feature transformations in another system. And that's scary, that's difficult, and sometimes not even possible. And if you get it wrong, well, maybe you're lucky and you get an error. If you're wrong and you're unlucky, you just get the wrong answers from the model. So this is, I think, where feature stores are aimed. Can we add a little more management around the inputs to our machine learning model to make some of these problems go away, improves discoverability and lineage, and also helps the models do more of their own homework, go get the features they need rather than push that to the caller. So let's feature engineer once and actually look up those values from wherever the model is used, rather than try to reproduce the feature transformation elsewhere. So yeah, again, you may say this doesn't sound a lot different than a table that you're managing carefully. And yeah, I think that's true. Feature tables, as I'll see in a brief tour here, are just tables with metadata and a little bit of extra API tool support around them. What they're trying to add are upstream and downstream lineage. Where did the feature come from? Where is it going to? And then how do I actually get that feature, that value at runtime when I might need it from somewhere else, from some diverse sources? So with that, I'm going to quickly give you just a taste of what that looks like in something like Databricks here. So I may start working on a telco churn problem. We won't go through the details here, but suffice to say, I'm starting out with some customer information and trying to figure out if it's enough to predict whether the customer will churn or not. That doesn't look like enough information. This is some basic demographic information that I might be starting with. And elsewhere, I can go grab the label. But the feature store might come in a case like this, where I know I want to go reuse some information that other teams have maybe already successfully used to predict stuff about customers. So the feature store, and in Databricks, it's actually integrated here, so you would see it in Databricks. Feature stores in general are lists of feature tables. That's what ours looks like, which are themselves just wrappers on tables. Oops, I clicked the wrong link there. Let me try again. Yeah, pardon, you can ignore that. So as I am writing my transformation code, if I instrument it a little bit differently, so I'll skip around here. If I take normal Spark transformation code, I might be running in Databricks to engineer features. If I wrap it up a little bit and manage this through the feature store in this notebook, then I get two things out. Number one, I would be computing features about customers and saving it to a table under the hood. So I would still see a data table of maybe service-related features about customers in my meta store. That doesn't change. But this would also appear in the feature store with some additional metadata on top. Things like, how is the table keyed? So feature tables are always meant to be joined. So they always have to have a primary key. So the relational model is sneaking back in here a little bit for this use case. What source data was used and read to compute these features? What code was run to compute these features? This is even a link to the exact revision of the source notebook. Who did it? When? When was this last updated? And then later, where are these features used? Here's the columns of the table. These are customer-related attributes, and who is using them? I can click through and find out more information about a model maybe deployed in production that is using this. And that might help me as a consumer of these features to understand what these features are and decide, yeah, I could reuse that. Or as the manager of these features, understand who I'm going to affect if I delete, stop producing something like this feature. So it adds a little upstream and downstream lineage. And suffice to say, this also integrates with the modeling process so that at runtime, if I want to build a model that reuses some of these nice features I found here in this feature table, and I'll fast forward and skip around a little bit. Not actually that hard. I would just run my same old training code, having enriched the input with the feature store and log it through MLflow. But then my model becomes data aware. It knows a lot about the data it needs to do its work, and it can go look it up on the fly. So later when I go to apply this model, actually I don't have to go look up all the features that it needs. I can just read a table of data, apply the model to it, and the model will go get all the additional data it needs, feed the model, make the prediction, and give me back the results. So that my production scoring job could be roughly this simple here. This is me applying the model I fit to some data where almost all this data is something the model decided to go add in because it needed it. And it's going to be quite simple. With that, there's so much more we could say. I'm tempted to tell you more about distributed deep learning, about AutoML, but this would make this more of a machine learning talk, not so much to talk about the lakehouse. I think the key points here are, this is important. So you can see this is a bit of a different world than the world of BI. And if we have a platform where we can do a bunch of things and not only support SQL and support security and proper data management, but also let people go run popular libraries, maybe on specialized hardware at scale as well, then we have a powerful platform. Then we open up a lot of the possibilities of machine learning without having to manage two separate environments for workloads that are ultimately fairly intertwined. Even here you saw the data science involves some data engineering, some feature engineering. These things aren't really that separable. And so the Lakehouse architecture has some promise for that. And of course, Databricks is a good example of that architecture. And so this is the kind of thing I wanted to show is possible. Before I close out, just maybe a reminder for those that are interested in learning a little more about the Lakehouse, or rather Databricks in particular, you can go, oops, where is our try? Well, I'll say just in passing, you can definitely try Databricks if you're interested for free. You can sign up for free and try it, our community edition, if you're interested in playing with this as well. And we'd be happy to help. And with that, let me unshare here, and maybe Jason, you and I can go take a quick look at Q&A here.
Yeah, I was trying to answer as many as I could. There's I was going to punt a few to you. This one is seems more like a, I don't know if it's a religious debate, but isn't machine learning a subset of data science? Like, I guess, like, we get all these terms that are like tossed around. There's like machine learning, data science, artificial intelligence. If you had to kind of like summarize how it all fits together, what's your definition?
Yeah, you're right. I think these terms are used almost interchangeably: AI, machine learning, and data science. So I don't know if there is a useful, consistent definition. Yeah, I think AI is probably the broadest scope, and then data science might be more of a, within the world of AI, which might include robots and playing games. Data science is things to do with analyzing data, and machine learning is maybe more specifically predictive models. But these are used so interchangeably that I tend to almost use them for as follows. I think of AI as like robotic dogs and playing chess. I think self-driving cars, data science as statistics, and machine learning as deep learning and things more similar to that. But they're kind of interchangeable.
All right. We had two questions I think are kind of similar. One is if, quote, the more data, the better. What about the famous statistics law of the power of sample? And then another question is that Gartner reports 70% of the industry is moving towards small and wide data instead of relying on huge data sets for AI. What's the take from Databricks? So you're kind of like talking to a lot of customers for their advanced analytics use cases. What are you seeing out there in the field?
So the first question was, what's the role of sampling in the world of big data? In theory, the idea is you don't have to sample anymore. Just throw more compute at it. A lot of statistics was developed when sample size n was 7, and we had to figure out how to correct for that. Now its sample size is 7 billion. So you can forget a lot of the statistics you learned, I guess. No, that's not true. That said, is more always better? Maybe not. I mean, sometimes more data isn't helping that much, certainly if it's noisy. Comically, a lot of the focus in machine learning and certainly in deep learning has been on bigger and bigger models, truly staggeringly expensive models, when very little of the focus has been on better data. So, and I think that's changing right now too. Just as an anecdote, I saw a paper that if you follow ImageNet, it's this image classification benchmark, and people keep spending millions of dollars to eke out another 1% accuracy on it. It turns out these massive models that are winning these days are doing so only because they're spending most of their time and energy working around errors in the source data, this fixed data set we've been using for decades. They have to learn so many parameters to basically memorize the mistakes in the source data. And if you can fix the mistakes in the source data, a much, much smaller model works. So that's a tangent, but I think just stepping back, I think there is a little more focus these days on better data, not necessarily just more data. Definitely some interest in active learning, like how can I intelligently figure out where to label my data, where the labels might be wrong, rather than just collecting more.
All right, and then I think the question was focused on like a statistical AI, but with deep learning, is it better to have more data if you're doing something around images or audio or video or things like that?
Probably. I can never say more. I would say in general, more data is better, but how much better it really depends. I think when you unpack it, it's, for example, if you are trying to detect anomalies, more pictures of things that aren't anomalous aren't really going to help. You're really trying to learn about anomalies. We're also, I think, entering an era of new questions about the data. Yes, this image classifier is 99% accurate, but where it makes its mistakes, it's pretty unfortunate. It's disproportionately affecting maybe a certain group of people. So are the models fair? Are they actually, are their errors distributed in a fair way? And that would lead you to ask more questions about not just the volume of your data, but the nature and distribution of your data. I'm sure we could talk for hours about this. It's not really specific to the Lakehouse, but important questions. And indeed, while it's nice to have access to scale, and probably more data is better, and it's nice to not have to worry about sampling, it's not somehow going to fix all the problems.
All right. And for feature engineering, are those feature tables you were shown, are those versioned?
Yeah, I apologize. Just in the interest of time, I didn't spend a lot of time going into the details. The feature store, at least in Databricks, is built on Delta tables. So everything you heard about Delta tables applies to these feature tables. The feature tables are really just metadata on top of Delta tables. So yes, you would get time travel in there. You can update the feature values and still go query previous states of the features as well.
Let's see.
Yeah, and also likewise, what was the value of that telecom demo? I didn't actually go through it. I apologize as well. The premise there was I want to build a churn model, which you might be doing or something similar. And I don't really have enough data, but if I reuse some features that were used by another team, I get a better model, maybe using AutoML to select models and then walking through the life cycle of how the features are managed, updated, improved, and used in models and then deployed. Is the perfect sample total population? Yeah, I mean, it still raises questions like if you, some group is 1% of your total population, and that means you're making egregious errors on that 1%, maybe that's not sufficient. Maybe you need to think about rebalancing your data set or weighting. And this is, again, a whole interesting ethics and explainable AI question. Checking questions here. I'm also looking at our backlog here. 1 minute.
There's one question. Does Databricks support textual ETL to convert textual data into structured data for ML use cases? And I know there's like a whole bunch of different libraries out there, but what are like some of the most common ones that people would use for that?
Yeah, one of the premises of this open-ish lakehouse architecture is you can really bring your tooling to the platform. And indeed, most of the work people do in data science won't be building tools themselves. They're going to be grabbing open source tools off the shelf and applying them. Same is true for things like NLP. There's great open source tooling in the Python ecosystem in particular for doing things like simple filtering, stemming, lemmatization, et cetera. And at the higher end for applying these sophisticated deep learning models that Google has trained on all the text in the world that it can really take text and digest it usefully.
There's one question I could take says this may be a strange question, but can a company build a user interface that doesn't require SQL and technology use Databricks? I think so. We've got a lot of different partners out there. Like I think ThoughtSpot is famous for basically just bringing a search box to your data, and then having you be able to search for something and then be able to quickly visualize from there. And you can hook that up to Databricks as well. I mean, essentially, if someone were to build a tool or a front end, as long as that tool can generate SQL that gets sent out to Databricks, then basically you can integrate it just like you could on any other JDBC ODBC connection.
Okay, Jason, are we through with the questions? Let me know when you want to wrap up.
There's one more that just came in. Is a feature store connected to MLflow to track the lineage of the data sets?
Yeah, so that's one of the nice things we've tried to do is integrate the feature store with a model tracking system like MLflow so that the models, when you track them, can be aware of a lot of the inputs they needed so they can go get them at runtime. So the short answer is yes, it's integrated with MLflow, and that's where the payoff happens. The logged model transparently goes and gets a lot of its own data.
Excellent. All right. Well, I think that was it. I don't know if you want to wrap it all up for us, Bill?
Yeah, sure. First off, I want to thank both Jason and Sean. I really appreciate the information you shared with us today. And we certainly appreciate the sponsorship and partnership with Databricks. In the last 40, the other thing, the questions that have been asked, not just today, but throughout the symposium, we plan on writing written answers, and we will send them out to everybody that has signed up for the event. In the last 4 days, we've talked about a lot of topics. We've talked about what is a data lakehouse. We've talked about lineage. We've talked about text. We've talked about visualization, housekeeping and future-proofing your data, governance, infrastructure, and machine learning. And I hope that we haven't overwhelmed you with too much knowledge at the same time. But if we have, well, that's not an altogether bad thing either. So I want to thank everybody for their participation, and I want to thank everybody that has viewed the event. And with that, I'm going to say thank you so much, and we'll, as they say in Texas, happy trails. We'll see you right down the road. Talk to you later.